All right, let's get started. Hello, everyone, and welcome to the 12th UQM virtual seminar. Today, we are very happy to have Mohammad Maghrebi and Abhinav Prem to speak about their latest research. So our first speaker is Mohammad Maghrebi from Michigan State University, and he's going to tell us about driven-dissipative systems, a critical tale of non-equilibrium phenomena. Mohammad, take it away.
Hi, so you can hear me, right?
Yes.
You can hear me and you can see my mouse. All right, thanks for the invitation, Hassan. It's been a pleasure, although it's a bit different. And also I noticed that you've started this series way back in December. So you've been kind of preparing for this. So, okay, in terms of the topic of my talk is a bit different. It's actually about ultra non-equilibrium matter, but Hassan convinced me that I should give this talk. And this is a wonderful audience. So, okay, so the main hero behind this work is really Jeremy, who's done really all the heavy lifting and all that. And this is a recent published paper in PRX. Okay, so let me start kind of high level. So imagine that we have a system. It could be a many-body system coupled to some bath. Now, the usual story is that if we wait long enough, the system equilibrates and it goes to a terminal state, which is just e to minus h over t. Now, if the system is driven, if the system is driven, the system rather goes to a steady state that's not really a terminal state. And roughly speaking, this is because drive and dissipation do not commute with each other. By the way, feel free to interrupt me at any point and ask me questions. Okay, so the dynamics for the system is just given by some Markovian quantum dynamics. There is a coherent piece to this, which is just the Hamiltonian, and this is a time-dependent Hamiltonian because there is something like a drive, such as laser, and there's also dissipative dynamics. So the question is really, what is the nature of the many-body state of the system? And I just told you that this is not going to be a thermal state. And in condensed matter, we would like to know what would be sort of the nature of phases and phase transitions in this, non-equilibrium steady states. And specifically, if we can identify any non-equilibrium phases and phase transitions, which are not available in equilibrium systems. Before I move on to the real content of the talk, let me just say this is not a theory's fancy. There are many, many experiments that just fit the description of driven-dissipative systems. Examples being Rydberg atoms, trapped ions, exciton polaritons, etc., etc. Now, just to give you an example, in exciton polaritons, these particles, polaritons are lossy. So in order to maintain a non-trivial steady state, the system has to be pumped continuously. And then this could give rise to interesting steady states, such as non-equilibrium BEC, for example. But this is just an advertisement for driven-dissipative system. This is, so I just move on to the outline of my talk. I'm actually going to tell you two stories. So both of them are driven-dissipative. One.
So, I ask you a question. Sorry, I don't know if it's allowed to ask questions. So
yeah, exactly.
Okay, Mohammed. So I'm just wondering, so what's the condition for this Markovian dynamics to be valid? So how do you know that this Lindblad stuff is actually valid? So it's not the fundamental equation of physics, right? So it has some applicability conditions. So what do you need?
Right, mainly there are actually two conditions. So one condition is basically, there's the Born condition, as there's a Markov condition. So, so I guess the question is about this equation. So one condition is that you have a weak coupling to the environment. And the other assumption is that, the system is Markovian, which usually means that you have sort of large bandwidths of the bath. And, that large bandwidths of the bath translates into a short time scale for relaxation. So often when those two conditions, Born Markov conditions, are satisfied, you have this quantum master equation.
One more question. Sorry, one more question.
Oh, go ahead.
On the same slide as before.
Okay.
So if I want to have a steady state, so this H is time dependent, rho is time independent. I assume D is also time independent.
Oh, yeah, that's a good point. Okay, so I'm partially lying here. So what you're gonna see later on in my slides is that I'm going to go to the rotating frame, which is satisfied under the conditions that I'm going to state. And in the rotating frame, it's going to be a steady state in the sense that dt rho in the steady state will be 0. Yeah, thanks for the comment.
So that's in some interacting picture. So in the Schrodinger picture, still the density matrix is changing.
Yeah, true. But it changes trivially with the frequency of the external derive.
Thanks.
Yeah, thanks for the question. Okay, so let me move on. I was just telling you that I'm actually telling you two stories. One involves a single order parameter, still a driven-dissipative system, but I'm going to argue that in this system, actually, despite the fact that it's very non-equilibrium at the macroscopic level, thermal behavior emerges and the phase transition in the system will be just an effective Ising transition, familiar in equilibrium. The second story, the more interesting one and also the more recent one, is when we have the competing order parameters. So they can be Ising-like order parameters. And I showed that indeed very interesting non-equilibrium behavior can emerge in this system. Okay, so let me start from the first story. I start from a simple model. The Hamiltonian is just the Bose-Hubbard model. It's not driven yet, it's just the Bose-Hubbard model. We have the hopping, there's the interaction. And if you want, you can imagine that we have sort of a system of coupled cavities. And this frequency omega 0 describes the frequency, the cavity frequency for each one of these cavities. Like I said, the system is not driven yet, and also the system is dissipative. Photons can be lost to the environment, or you can call them bosons. But this system is not so interesting. I mean, if the system is not driven, it just goes to a boring, trivial empty state. Now let's make it more interesting by driving the system. Imagine I drive the system with some amplitude omega, the Rabi frequency, and some frequency that's very close to omega 0. So now I can go, if this frequency is much larger than everything else, I can go to a rotating frame in the Hilbert space, and then this frequency, this time dependence is actually gone in the rotating frame. That's the point of going to the rotating frame. And the frequency here is actually replaced by detuning. Now, in a situation that detuning is comparable to J, comparable to omega, the frequency of the drive, and the rate of dissipation, things can become interesting, and this steady state is certainly non-trivial. Okay, I don't see my, okay, so this is also for the reference. This is the Lie-Medal type equation to describe the system. Okay, so the starting point to understand what's going on is mean field. It's just simple, so let's start with something simple. It turns out this is the phase diagram at the level of mean field. So at the small values of omega here, we have a steady state that has a low density of bosons or photons. That makes sense. If we go to larger values of a drive, then we would have a high density of photons. But in between, there is this region that at the level of mean field, there are two stable solutions. So this is sort of the many-body analog of optical bistability. And one more fact is that as you go inside this region from this cusp-like point, it actually becomes something like a continuous transition that you go from one solution to two stable solutions. Okay, before I continue with the theory, let me—
I have a quick question about the previous. So where does the interaction come into this story?
So the interaction goes into the mean field equation. On a couple of slides later down the road, I will show you the mean field equation. So that's already being incorporated in this equation.
Like if you make the system, like if you decrease T over U, or is there going to be any change to this phase diagram?
Oh yeah, well, so one thing that I should say that here I take, on the technical side, I take U, the interaction, to be a small. So J can be large, but I treat U to be a small, because at the end of the day, the most controlled situation that I can say what I want to say is when U is perturbative. So let's say I limit myself to a small U, that the semi-classical approximation will be justified later on.
Okay,
maybe I missed. Did you say you have one particle per set or something?
Oh no, I can have many particles per site.
But
I have one cavity per site, but each cavity can have many photons. And in fact, that's the regime that I want to put myself in.
So in the Bose-Hubbard model, if you have some fractional filling factor, you will not have an insulating phase.
Yeah. So one thing I want us to appreciate is that once you're in the realm of non-equilibrium, then we shouldn't really think about the ground state. This is we're actually going to think about the steady state of the system, and that can have just very different properties. And also, like I said, U can be a small. So, and the system is also being driven. So there's also this linear term. Okay, if there are no further questions. So this is sort of kind of a very simple mean field phase diagram. And on this slide, I just make a point that this is also very experimentally feasible. Just to go back to an example that I mentioned before, in terms of exciton polaritons, you see that as a function of power. For a small power, there's only a single solution. For large power, there's a single, high density solution. In between, there is a region that you see this bistable behavior. Okay, so going back to the model, as we approach the cusp from one end, it looks like that we have a continuous transition, that one solution actually goes continuously to two solutions. So this looks a lot like the Ising transition, but can we actually make this precise? So this is what I'm going to do here. So now going back, let's be more precise about the mean field equation. This is alpha is just the expectation value of this bosonic operator. And this is the mean field equation. And you can see various terms, the tuning, dissipation, and so on. And there's also the white noise that comes from the fact that I have dissipation. Kappa is the strength of dissipation. So this is the mean field equation. And this actually looks a lot like an equation that gives you a thermal equilibrium. So if you have a Brownian particle that diffuses around, subject to some energy functional and some noise, eventually it goes to a thermal state. So the mean field equation is kind of similar, but it's not quite the same, because this cannot be extracted from a potential, at least not from a real valued potential. So we don't have this equation that we want for thermalization, not just yet. So to understand this, let me look at the dynamics in the phase space. So here on the right, I have the phase space, real part of alpha and imaginary part of alpha. And this is the dynamics. So everything just approaches to this single solution. When I'm in this region, in this region, there's a single solution. Everything approaches to this point. Once I go inside this region, I find two new stable solutions, and this solution becomes unstable. So one thing to notice here is that the dynamics along this direction is kind of fast, while the dynamics along this direction is kind of slow. So by identifying sort of the gapless field and the gapped field, we can just integrate out the gapped field. And this gives us something like this Ginzburg-Landau free energy. And we can indeed show that the phase transition is kind of like the Ising transition, and is described by Ginzburg-Landau kind of paradigm. So the bistable region that I mentioned before at the level of mean field is actually replaced by a first order phase transition that ends at the critical point. And you can think of this as kind of a liquid gas transition. So gas for the low density and liquid for the high density. So again, it's kind of interesting that although the system is really strongly driven from equilibrium, as far as the phase transition is concerned, it's really described by an effective thermal Ising behavior. So this is the end of the first story that I want to tell you. But then this is interesting, at the same time is disappointing a little bit to see equilibrium again showing up in a very non-equilibrium.
I have one more quick question.
Sure.
So what is what is the, I don't know, operator or parameter which plays the role of like magnetic field in the Ising? Like you have this line of the first order transition.
True.
It's really a combination of drive and dissipation.
Right. So it would depend. Yes. So in that sense, drive certainly affects the shape of the phase diagram, the boundary. It would certainly affect the shapes, but it would not affect the universal behavior. So the liquid gas transition is also in the same universality class of the Ising transition. It's just that you have to define something like the density as or the difference in the density as the order parameter. So it's not that the drive is not important. It's just that it doesn't affect the universal properties and also like the critical exponent and so on, which I will talk more about in the sort of the second half.
So how do we know fluctuations beyond mean field is not important?
I mean, fluctuations are actually considered. I don't show them here, but the fluctuations, you can also include the fluctuation in the same picture. So it would be a kind of, model A type dynamics, which is governed by kind of Ginsburg-Landau energy functional, and there would be some white noise. But we know that the universality class, even including fluctuation, the universality class is not changed. It's just the equilibrium model A. Okay, so if I want to finish in time, I mean, I actually enjoy the question very much, but let me just move on so I get to the better part of the talk. Okay, so now I want to kind of find a situation that it looks like that when I have the Ising-like order parameter, the dynamics is too constrained and it doesn't look like that it leaves too much room for non-equilibrium dynamics, at least critical non-equilibrium dynamics. So let's imagine a situation that we have a more complex order parameter. So this is pretty much the same model. It's driven. It's kind of like the Bose-Hubbard model, except that now I have, instead of on-site Hubbard interaction, I have nearest neighbor repulsive interactions. That's the only difference. And also I have dissipation just as before. But what makes this model interesting is that it actually has two distinct many-body tendencies. On one hand, it has just the same kind of, dark, bright, or, gas, liquid kind of transition. On the other hand, when the drive becomes large in this region, there is a large population on each side. And because of the repulsive interaction, the system has a tendency to become an antiferromagnet. So these two transitions could happen at the same time. Now to define the order parameter, we can consider the two checkerboard sublattices. So bias stability order parameter is kind of like the average of the density or the average of the field, while the antiferromagnetic order parameter is kind of the density imbalance. So just like before, I'm going to skip all the details, all the dirtier stuff, but we can identify the soft modes that are responsible for the phase transition. So we have one soft mode for the bias stability phase transition or liquid gas phase transition, and one soft mode for the antiferromagnetic phase transition. And when we put them together, in principle, we can have a multi-critical point that's now actually described by a Z2 by Z2 symmetry, and things can become much more interesting at this point. So if we want to write down the simplest kind of dynamics for this model, if the two phase transitions are far from each other, they're decoupled, and we pretty much have the same paradigm. We have some dynamics, there's some energy functional, and there is some noise. But in general, they would be coupled to each other. So phi2 affects phi1, and also phi1 affects phi2, but possibly with different coefficients. So you notice that I have two different coefficients, G12 and G21, the way that the two fields affect each other. Now, if they just happen to be the same, if G12 is the same as G21, you can see that these terms, they can just be extracted from an energy functional. So I can just absorb these two terms in a term in an energy functional, and I'm just back to equilibrium. But in general, there's no reason that they have to be the same. And in fact, in our macroscopic model, we can compute this, and they're not the same. So then the question is, what happens or what is the behavior of the system? To understand this, it's actually more useful to map the model to what I call the two-temperature model. So here I just copy paste the same equations. I also include the noise. So there is the usual terms, the coupling, and the noise, which is white noise. But now notice I have a scaling for them. I can scale, let's say, phi2 by a constant, and that would result in scaling G12, while G21 is just remains unchanged. So by making this scaling transformation, I can bring the values of G12 and G21 to the same value. So I call that G tilde, just not to confuse you. So now it looks like that I can have Hamiltonian dynamics because I can bring them to the same value, but there's a catch. The catch is that now the two noise will have different temperature. So notice that each kind of noise describes the corresponding field. So if colloquially speaking, I call this a temperature, it looks like that I have two coupled Ising order parameters, each of which lives at its own temperature. So by making this transformation, I kind of map the physics in the ratio of G12 to G21 to the physics of the ratio of T1 over T2. So now I have to say something about a two-temperature coupled Ising model. Okay, so what happens if T1 is not the same as T2? And this means that at the macroscopic level, this dynamic is very non-equilibrium. I mean, it can't be more non-equilibrium than that. They're just two temperatures. But the question is, could equilibrium restore itself somehow at the macroscopic level, at long wavelengths? So to find the answer to this question, we have to do some hard work. We have to do some RG. There are some technical challenges. Okay, let me just move on. I don't think I have enough time. Let me just show you, just to whet your appetite, let me just show you some diagrams here that in order to compute the RG, you have to compute diagrams like this. And in fact, we have to compute two-loop diagrams just because that's what gives us the RG for the ratio of the two temperatures. And often when you see these diagrams, you just want to scream and run away. But then there comes Jeremy, and he will just compute all these diagrams for you and much beyond. So in the end, let me just report kind of the RG equation. And this is a very simplified RG equation. But I think that's really tells the story. So we can just go ahead with this. So V is, I just defined as the ratio of the temperatures. And we can compute this, and it just becomes the equation that you see here. Now, a few points about this is that this is only non-trivial if G12 is non-zero. That makes sense, because if there is no coupling between the two fields, they don't care if they live at different temperatures. Okay, the other interesting observation is that the only fixed point of this RG equation, the only physical fixed point is when V is 1. And that means that T1 is the same as T2. Not only that, but also temperature is scale invariant, meaning that if you compute this gamma function, the flow of the RG flow of the temperature, or what I call the temperature, which is just simply the noise, is just 0. That means that temperature is scale invariant. That's exactly what you would expect from temperature, that different partitions of the system, they just all see the same temperature. And these facts together, they mean that the system, although very non-equilibrium at the macroscopic level, reaches equilibrium at long distances. And one more thing is that this fixed point is actually a stable fixed point, is even robust against non-equilibrium perturbation. So let me show all of this to you in a different picture. Now I go back to this G12, G21 space. So remember, I had two representations, one in terms of the two temperatures, one in terms of these original variables, G12 and G21. And let me just remind you that when G12 is the same as G21, I can just write everything in terms of an equilibrium picture. So that's the equilibrium line. But what I just showed you in the previous slide is that there appears to be only a single fixed point. And this fixed point is the ultimate fixed point that describes the long distance behavior of the system. And one more fact is that this actually, it says an emergent O2 symmetry despite the Z2 by Z2 symmetry. But most importantly is that this is sort of the stable fixed point. It's even robust against non-equilibrium perturbations. Now, this is remarkable because it shows that equilibrium behavior still is very persistent, but this is not really the end of the story. So, again, let me just move on here. So what happens if G12 or G21, either of them, is negative? Let me just quickly go back to the scaling argument that I had. If I scale phi by constant, then G12 goes to a new constant, but the coefficient here is positive. So by making this a scaling transformation, I cannot change the sign. So I cannot map this problem if I'm in these two regions that either of the two is negative. I cannot map it to this quadrature that both of them are positive. So one possibility is that if I start in these quadratures, they just, under RG, they flow back to its equilibrium fixed point. But that cannot be the case for a simple reason. If, imagine that you are at this point that G12 is actually 0, that means that the field phi1 is just causally disconnected from phi2. It's just unaffected by the field phi2. So the RG flow cannot take me from one quadrature to another one. So this presents an intriguing possibility that I can have a non-trivial fixed point, which by necessity would be a non-equilibrium fixed point in the same quadratures. Okay, so let me actually show you that this is indeed the case. Although we don't have this Hamiltonian dynamics, but we can still use this scaling transformation to bring the absolute value of these variables to the same value. So, okay, this doesn't exactly give us Hamiltonian dynamics like this, but this gives us something that looks similar to this. And this is kind of interesting because it means that while phi1 is pushed by this coupling, phi2 is actually pulled by the same coupling. So you can see that this is just at the outset is very, very non-equilibrium. And again, I can map the ratio of the absolute values to the ratio of the temperatures. But I just emphasize that even if T1 is the same as T2, the dynamics is very non-equilibrium just because of this structure. Okay, so I can, or Jeremy can compute the RG equation again, and we kind of, not exactly, but kind of find a similar RG equation. It turns out the fixed point is again at V being 1, which means that T1 is the same as T2, but in terms of G12 and G21, it means that they're negative of each other. So that actually confirms this picture, that I have these fixed points that G12 and G21 have opposite values. And interestingly, this time you can see that temperature is not a scaling invariant. So this gamma factor now actually is not a constant. That means that temperature itself is scale dependent. Now, you might object, what do I actually mean by temperature? This is a very non-equilibrium system. So it's true that we don't have an intrinsic notion of temperature, but we can use fluctuation dissipation relation to find an effective temperature that can be possibly frequency dependent. So in the spirit of fluctuation dissipation relation, we can divide fluctuations by dissipation, and this gives us possibly an omega dependent effective temperature. Now, in an equilibrium system, at high frequencies, there might be some non-equilibrium features. But if an equilibrium fixed point is the ultimate fate of the system, eventually this effective temperature goes to a constant. Then we go to low frequencies and long wavelengths. But for a non-equilibrium system, or non-equilibrium fixed point, rather, I should say, you can see in this case that the temperature becomes omega dependent and remains omega dependent at all the scales. And in fact, it even diverges as omega goes to 0. So in a way, it just, the system gets hotter and hotter as we go to longer and longer distances. Okay, I have a couple more slides, but Hassan, please free to stop me at any point that you want. I think it's just a couple of more slides. So another interesting feature of this fixed point is that there are some log periodic oscillations. So this is the RG equation for R1 and R2, which describe the distance from the critical point. And this is the RG equation that we find. And you can notice that the eigenvalues of this 2x2 matrix are actually complex valued. So this is interesting. The real part just gives you the famous exponent nu that characterizes the dependence of the correlation lengths on the distance from the critical point. But the imaginary part actually gives you these log periodic oscillations. That if, for example, you look at correlation functions, there's a piece that depends, there is a periodic dependence on log x. And this itself leads to discrete scale invariance. So to see this, let me first show you what the usual story is, that at the critical point, you have critical fluctuation, things are scale invariant. If I scale the system, the correlation function just, is a scale invariant, just picks up a constant factor. But when you have these log periodic oscillations, under a scaling of the system, you have this kind of a scale invariance only for discrete values of B. And this is related to this exponent beta. So similar pieces of physics happen elsewhere. Efimov states is one example. Earthquakes is just another, maybe not so familiar example. But what makes this kind of unique is that this is really a many-body system, and this is also in a non-equilibrium setting. Okay, this is really my last slide. I just, this log periodic oscillations kind of translate into the shape of the phase diagram. So there are 4 different phases: disordered phase, antiferromagnetic phase, bistable phase, and the doubly ordered phase. And I just want to show you a little animation here that shows that we have the scale invariance here. So if we just take the same picture and scale it down, after a certain discrete scaling, you can see that the phase diagram just maps onto itself. Okay, since I'm over time, let me just go ahead. This is just a summary. I will skip it, and I will just leave you with this. And thank you for your attention.
Thank you so much, Mohammad, for this interesting talk. So now we have like few minutes for maybe some quick questions.
I have a basic question.
Hassan, decide who should ask.
Yeah.
I don't know the second person. I just heard Liu Jun.
Okay, then I'll ask. So in the talk you mentioned, there's this Ising type transition and the O2 type transition. I just want to make sure, when you, do you mean these are described by Ising CFT and O2 CFTs?
In 2 dimensions, yes. Actually, I guess right.
Into space-time dimension.
Right. Yeah. I think the question was that O2 fixed point is described by CFT.
Is it?
Yes, I think it is. Yeah. But the one thing I should say is that the non-equilibrium fixed point that I described, which is not O2, that only exists in 3 dimensions. This is kind of a side comment, but.
So you mentioned in some case the dissipation is unimportant for the universal physics. I assume you mean dissipation is irrelevant with respect to the CFTs?
So dissipation in this picture, no. So I did not mean that dissipation is irrelevant. So dissipation in this case actually gives rise to this kind of white noise kind of fluctuation in the system. And that's kind of, in the end, that's what gives you a classical behavior. And in the case of the effective, thermal Ising behavior, that's kind of response. So there would be an effective temperature that's kind of proportional to dissipation in the system. So I didn't mean that dissipation is not relevant, but in that case, what I meant is that although you have non-equilibrium drive in the system, so it was more a point about the non-equilibrium drive rather than dissipation, that the non-equilibrium drive does not change the universality of the system or the universality of the critical point.
So whether it changes the universality class is purely a property of the CFT itself. So you can, just by looking at the CFT, can you directly see it?
I'm not sure. So before we get to the CFT, we have the microscopic model is not really conformal invariant, right? So,
sure.
but by the time we get to this effective description, it's just the same effective description that we have in an equilibrium. So that's just the same exact effective description.
Oh, that's what you mean. I see.
Yeah.
Mm-hmm.
Okay, Paulo, go ahead.
I have a basic question about the plot of the effective temperature. a low frequency. You have this divergent behavior with some exponent, yeah, this omega to the minus gamma t. Is this a generic feature of non-equilibrium fixed points?
Oh, far from that. For most examples that I've seen, for actually many examples that I've also been involved, in many cases, this first feature is more, this first feature is actually more kind of generic, that often you find an effective temperature. So this is, I would say, this is very non-generic. I know of only a couple of examples that feature something like this.
So I guess, I mean, if I have a fixed point that doesn't follow the blue line, does it have, like, would I expect it to follow the red line, like something like the red, like a power, power divergence, or there could be something else as well?
Oh yeah, no, that's actually this line that you see here. That's the line for this non-equilibrium fixed point.
Yeah.
Right. So, sorry, maybe I missed the question. Can you repeat the question?
Yeah, I was just wondering if this qualitative qualitative feature is the only alternative I can expect to the blue line.
That's a very good question. So I would say that one thing that's kind of hidden everywhere in this talk, that all the statements that I'm making, they apply to the critical point of the system. If you're far from the critical point or the phase transition, I mean, the story can be very different. Now, kind of narrowing your question a little bit about the critical point, there's another possibility, which actually I just recall that also occurs, is that you can have an effective temperature that instead of curving up, it can curve down. So that's also a possibility. Yeah. If you want, I can provide some references. But yeah, but that's in general, that's a good question. What are sort of the zoo of different kind of behaviors that you can have here?
Thanks.
Sure.
Okay, Apinoff, do you have a question, or you want to set up your slides also?
No, I had a quick question about sort of this starting point. So you're starting with Lindblad dynamics, and there I would have expected that you get a periodic steady state. So I'm just wondering about sort of the accuracy of mean field, and do you reproduce that steady state as you take higher and higher corrections into account?
Right. So once I go to the rotate, you're right. I start from a time-dependent Hamiltonian. But since the frequency is very large, is actually much larger compared to everything else in the system, I can safely go to the rotating frame, and in the rotating frame, I can just make these statements that I make. So this is kind of this uses the fact that the frequency of the drive is much larger than all other energy characteristics of the system.
So if you do sort of numerics on small scale systems, you would expect that Lindblad dynamics matches what you see, because I'm just wondering about sort of, now you're simulating a, effectively a nonlinear classical system, and here you can get all kinds of different behavior. But at least in Lindblad, regardless of what the driving frequency is, I would expect that you just get a periodic steady state, which is synchronized to the driving frequency. Okay.
Yes.
Okay, well, let's thank the speaker again, and let's move on to the second talk of today. Thank you, Mohammad, again.